Hello, good day, everybody. Thank you for all joining this next webinar we are hosting today. It's in the series of repeating the PA basics, and this is, I think, now the fourth or the fifth webinar that we have around this topic. So today we will talk about sound design for speech intelligibility. Today again, Jan-Pieter Smolders, my colleague from Eindhoven, application engineer public address. Today he will talk about speech intelligibility. Jan-Pieter, I give you the word. Please take it away and educate us on speech intelligibility this time. Thank you.
Okay, thanks, Maarten. Welcome, everybody. Today's topic, speech intelligibility, and in specific, how can you improve actually speech intelligibility in a certain room? Which measures do you have to take? The topics of today are the speech signal, signal to noise ratio, direct to reverberant ratio, delayed arrivals, and at the end we'll go into the speech intelligibility and STI measurements. So what influences speech intelligibility? For instance, background noise, like noise like from trains or people even talking in a room, air conditioning in an office, things like that. Those kind of noises will have a bad influence on intelligibility. Now, for signal to noise ratio, the lower the sound pressure level, or let's say the level that is coming from your loudspeaker, and the larger the distance from a listener to a loudspeaker, yeah, these levels will go down. So the signal level compared to the noise ratio to the noise level will go down. So it's important to know at what noise level your environment is. Those measurements you have to take. Then the materials used in a room, they cause reflections, so reverberations in a room is very important. They can be they can have a negative influence on speech intelligibility as well. And then you have to think of materials like glass and concrete, marble, so hard materials that reflect the sound. And also delayed arrivals. That is sounds that are perceived as echoes, like in large buildings where when you stand in the middle and there is sound, or somebody closes the door or something like that, and that echoes around. You hear, let's say, well, kind of a hum from the back of the from the building. So delayed arrivals have also a negative influence on speech intelligibility. Then, of course, the sound system. If you have a bad sound system design, for instance, not enough loudspeakers, or the position of loudspeakers are not good, that can also be well, having a negative influence on the intelligibility. How can you improve intelligibility? A very good way to improve intelligibility is improve the room acoustics. For instance, yeah, using sound absorbers, like you see here on the right. You know, these materials are often not liked by architects, for instance. They don't want these things visible in their construction. Or you can improve the sound reinforcement system, for instance, by using these column speakers like you see here on the right. So you can aim it at where the people are standing or sitting. So aim it to the listening area. And with that, you will avoid reflections from, for instance, the ceiling or the walls. How does this work? Reflection and absorption. Here on the right side, you see a picture where the incoming sound is hitting a wall, a marble wall, for instance, and then it's reflected. And the absorption coefficient is a measure of indicating how well a certain material can absorb or reflect the sound, actually. So with a high coefficient, this material is very absorbent, and with 0, it will reflect all energy that is put in onto that wall or to that material. Yeah, hard surfaces like glass and marble, they have a low absorption coefficient. That means they, when sound is coming into that wall, it will reflect most energy. It will be reflected, so the sound will be reflected from that wall. And they, of course, have a negative influence on the speech intelligibility. Now, if you have a room or a wall that is not flat, so if you have a rough surface, the incoming sound is reflected in many directions. So it's not evenly reflected, but it's scattered all around. That means that the energy of all these reflections individually are lower compared to a reflection that is direct from the wall, from an even surface. So this is a little bit better if you look at the influence of reflections in terms of intelligibility. This material, a wall like this, will have less influence on the intelligibility compared to a flat wall, a complete flat wall. If we look at the sound reinforcement system, the only thing that a sound reinforcement system can have influence on is the transfer part from the loudspeaker to the human ear, to the people who are listening. That's the only thing it can do. So what is important then to know, the coverage of a loudspeaker. We have seen the coverage area or the opening angle of a loudspeaker. So you have to know how many loudspeakers are required to cover a certain area. And also it's important to know how well a loudspeaker can reproduce all frequencies at the same sound pressure level. So we have these frequency responses of the loudspeakers. They are important as well, at which sound pressure level they can reproduce all frequencies in the same way. And another thing, the loudspeaker, we have looked at it also, the loudspeaker has to be able to reproduce a sound level that is higher than the noise level. Otherwise, you will not be able to distinguish a message from a sound system that is spoken. It will be the same level as the noise. You will not hear what somebody is saying. And the last thing is quite important, directivity. So we have to be able to position the sound where people are listening, so to the listening plane, to the listening area, like for instance with a column loudspeaker. Now, what is the added value of a sound reinforcement system with digital signal processing, DSP? The DSP inside a sound reinforcement system, you can fine-tune the sound that is coming out of a loudspeaker. Now with EQs, EQs that are inside the equipment, you can influence the frequency response of a loudspeaker by adjusting them in a certain way. Like you see, for instance, here on the right, you can gain some frequencies, or you can, let's say, lower some frequencies, so that the response of the loudspeaker will become more flat. Now, one thing to keep in mind here, if you gain the frequencies, certain frequencies, you will stress the loudspeaker. So be careful when you're doing this. Don't overstress the loudspeaker with gaining up some frequencies, right? Then another thing what you can do with EQs is cover some room mode. So room mode is, each room has a fundamental resonance, and depending on the size of a room, they vary in the frequency from 20 hertz to 200 hertz. That's all based on the size. And if you have, let's say, a certain frequency in a room where it starts to resonate, you get standing waves in the room, you can take those frequencies out. So if you maybe you have been to a concert once and where the sound technician is doing some sound checks, and then all of a sudden you hear such a low humming sound, that's most likely then the room mode, and he will take it out. He will take it out with EQs. Now here you see the pictures on the right, the EQ sections of Paviro and Presenza. Both systems have this kind of DSP on board. Okay, if you look at the signal path, yeah, we know the speech signal consists of vowels and consonants. The vowels are typically in the frequency range of 1 kilohertz, and consonants between 2 and 4 kilohertz. And the consonants are most important for speech. And if you look at the speech spectrum, the around the 500 hertz, the speech has a maximum. If you look at the picture on the right, you can see around 500 hertz. Sound pressure level of that frequency is at the peak, is at the top. Now, if you look at the 1 kilohertz where the vowels are, that is actually the power of the sound of the spoken word, and the area of 2 to 4 kilohertz, the consonants, they don't contribute to the speech power at all. Yeah, you have to look at it like this. You try to shout the letter P, for instance, you cannot do that. Like an A or an E or O, you can shout it out. You can put a lot of power in it, but a letter P, that will be difficult, right? Now the frequencies, like I said, between 2 and 4 kilohertz, they are contributors to the speech intelligibility. The other frequencies, so frequencies below 500 hertz and above 8000 hertz, they do not contribute to the intelligibility that much. If you look at the EM54-24, there's also a graph like this, where a loudspeaker has to comply to a certain area that it has to reproduce a sound at a certain sound pressure level. So if you look at this graph, you see the red line, that loudspeaker. If you look at the area between 500 and 8000 hertz, that's the most important part. The speaker with the red graph, so the red performance, is okay. It's in the non-shaded area. While the speaker with the blue line, you can see here on the right, it already drops at around 3,500 hertz, around 4,000 hertz. That means that this loudspeaker cannot reproduce a sound for those frequencies at a high enough level, so that speaker will not be certified. Then the opening angle of a loudspeaker. When a frequency is higher, the opening angle becomes smaller, like you see here on the picture below. If you look at the left side, at the low frequencies, well, the lower the frequency will be, it will spread around the room, and the higher the frequency is, it will be more directive. You see here on that picture. So this 4 kilohertz opening angle is the frequency you should look at when determining the amount of loudspeakers. So you position them in a certain distance from each other, cover the listening area properly. Another option is to group loudspeakers. So if you put, for instance, 2 loudspeakers like you see on the picture on the right next to each other, that also means that you can aim it to a certain area, and with that you can also increase basically the opening area or the coverage of these loudspeakers. One thing we also looked at in the previous webinars, sound pressure level and distance. We know that the sound pressure level is measured at 1 meter. This is specified in the IEC norm 60268-5. So it's measured at 1 meter, and the physical consequence of moving away from a loudspeaker, if you double the distance, the sound pressure level will decrease with 6 dB. If you have a point source like this, you double the distance, the sound pressure level here on axis from the loudspeaker in this picture will go from 90 dB to 84 dB. If we would move 4 meters away from this loudspeaker, then the result would be 78 dB and so on. Now for a line source, a column loudspeaker, this is different. When you double the distance from a line source, the sound pressure level will be reduced by 3 dB. This is important to know. We look at the noise levels and sound pressure levels from a loudspeaker. You have to understand that this will be the result if you move away from a loudspeaker. If it's high up in the ceiling, for instance, you have to know what the distance is, and then you can determine actually the sound pressure level on the listening plane. Signal to noise ratio. Yeah, there are different environments have different noise levels. You can imagine, for instance, here in the pictures on the right, the museum, it's very quiet. There is almost no noise. While in a railway station or swimming pool, the noise, the background noise levels are pretty high. Then if you go to a factory, for instance, that could go up to 100 dBs or more. So it's important to know what your noise level is. I have a recording of noise in a tunnel, where you can have higher traffic loads, and also, like you see here, these the ventilation on the top. They produce also noise, so that can go up to more than 90 dBSPR. Now I would like you to hear, if I can see, I will show you or let you hear this sound with a low sound to noise ratio. I'll share my recording, just a minute. Share this file. So this is a signal with a low sound to noise ratio. Here it comes. Was that audible, Maarten?
Yeah, I could hear it.
Okay, I will play it once more. So listen to carefully. You will hear the fans actually on the foreground, and on the back, way in the back, you will hear the announcement. Here it comes again. Okay, the next I would like you to hear is a recording with an improved sound to noise ratio. So this is a better recording where the sound to noise ratio is higher. Here it comes. Open this file.
Please leave by the nearest exit.
Okay, I will play it once more.
Please leave by the nearest exit.
So this is an indication of a good and a bad sound to noise ratio. At first recording, it was not really audible what the message was, and you can imagine if there's traffic inside of a tunnel like this, the sound to noise ratio is even worse, right? So these are challenging environments where you have to make sure that your sound level, or the signal that comes out of the loudspeakers, is higher than the noise level. Now, for a good speech intelligibility, sound to noise ratio of at least 10 dB is required. That means that the sound that is coming out of the loudspeakers at listening height, the listening plane, must be 10 dB higher than the noise. Now, if the SNR, if the sound to noise ratio, is higher than 15 dB, then the noise has no influence anymore on speech intelligibility, and you can ignore it. So if you can reach that in your environment, then you have a very well speech intelligibility. Yeah, they assume that in most cases the noise level is constant. So you make a measurement of the noise, and that's noise level then. And then you with those figures you will design your sound system. The noise level is not always equal. Over time, it can change. Like for instance, if you're on a railway station and there's a train coming in, then the noise, of course, goes way up. So it's not constant at all times. So that means if the noise level is constant, then the announcements will be clearly audible when you have this 10 dB signal to noise ratio. But if then a train comes in, then this sound or this message can be inaudible due to the noise level that is increased. Now there's a way to solve this issue with AVC, with automatic volume control, like you see here on the right from the Vari loudspeaker. What does it do? It will increase the volume if the ambient noise is increased. So at a certain threshold, you can set that in a system. The volume of your sound system will increase. So you can set that in certain steps, certain ranges. You can increase the volume. Now, some of the systems have this AVC functionality inside, like for instance, Presidio. You can use AVC, but you will need a sensing microphone. That means that you need a microphone that is actually at the location where you do the measurement. So you have to install a sensor microphone in order to measure the noise level. Now with Presenza, we also have this noise sensing microphone, the ANS, ambient noise sensor, and you can use it in combination with the Presenza system. So that's convenient. You just plug in and connect the ANS to the Presenza system, and you can use it. There's also a loudspeaker that has AVC functionality inside. The Vari directional array has this. It has a sensing microphone on the front of the loudspeaker, and you can set the levels also in the configuration software, like you see here on the right. Distance to a loudspeaker. Yeah, we have already talked about this. It's important to know the distance and the sound pressure level that a loudspeaker can deliver. A point source, if you double the distance, like you see here on the right, the sound pressure level is reduced with 6 dB, and for a line source, like a column, it is only reduced with 3 dB, and that's due to the construction, like you see here on the right. The coverage of the sound of a point source is larger compared to a line loudspeaker. So be aware that the signal to noise ratio, that your signal is always at least 10 dB louder than the noise. And if you know the distance, make sure that your loudspeaker is able to at least deliver 10 dB more sound pressure level than the noise in the environment where the people are standing or listening. Now there is modeling software available on the market where you can calculate sound pressure level at the listening plane. You see here on this screen, you see two examples. And here you can make a choice of the type of loudspeakers that you want to use. For instance, on the left side, you see a lot of ceiling loudspeakers covering this whole area. And on the right side, you see the vari-directional array. Here on the side here, just one loudspeaker also covering the area. So this also might be a reason to choose for maybe an array instead of a number of loudspeakers, where you can save on installation costs and maybe also the cost of the amount of loudspeakers. Direct to reverbant ratio. Okay, we go talk a little bit about room acoustics. It's actually common sense if you look at the propagation of sound through the air in a room. You can see here on the right side, somebody is talking. He's talking to a person opposite to him or her. Then the sound also travels to the side of that person, and it will hit the maybe the ceiling, the floor, or the side walls, and that will also propagate to that room, and it will also reach that person, but then delayed in time. It's not at the same time at the listener's position. So we're talking here about early reflections and reverberation. So the sound that is from the back of that person coming from the back wall. Now the level of early reflections and in reverberation increase when the room is finished with hard materials. Like I already explained, materials like glass or marble, you will have a lot of energy coming back from those walls. You can see that here on the right side, the early reflections, the green bars you see there are early reflections, and they have still quite some energy in it. So they will influence also the level of sound that is reaching the person listening. What is the effect of reflections? Okay, we have the direct sound, so the person talking. That's at a certain level. Then we have the early reflections, so the reflections from close to the person talking or the loudspeaker positioning, and they will give you a kind of an idea on how big the stage is or the room is, and how wide it is. It will give you well an idea of that room size. The late reflections, yeah, they are actually a lower level, the low level energy that's coming back, maybe from the back of a room, and it's well not audible anymore. What is there is most likely low frequencies that are still there, and they will have a bad influence on the intelligibility. RT60 is a measurement you can do in a room that will give an indication how long it will take for the sound pressure level to reduce with 60 dB. Well, in general, if you have a long RT60 time, it means that you have a lot of energy in the room and maybe also a larger room. Now, if you increase the reverberation and the reverberation time increases, now the result will be the direct to reverberant ratio will decrease, and it will have a bad influence on the intelligibility. Now, if you have treated the room with absorption material, so they will reduce the reflections, they will contribute to the intelligibility, of course. So if you can take away these reflections and reverberation, especially reverberation, then it will help you increasing the intelligibility a lot. So what you can also do is maximize the direct to noise ratio. So avoid reverberation or reflections from the wall and ceiling. Like you see here, for instance, a high directive loudspeaker like this column over here. You can point it at the listening plane, so avoid reflections from the ceiling, from the ground floor, from the walls. So in that way, you can optimize the direct sound and provide the sound only to the place where it's needed. So that's one thing you can do with loudspeakers: avoid reflections, and don't aim at the walls or ceilings or hard construction materials like marble or glass. Don't aim it to concave constructions. You can imagine if sound is Like you see here on the right, if sound is traveling into a concave construction, it is reflected to the central point here. So here, around here somewhere, you will have a lot of energy coming back from that construction. Aim at absorbing or scattering areas that the reflections are scattered around the room. And the best thing to do is to aim at the audience where people are sitting to the listening plane. An example here in this picture, you will see a varidirectional array. With the configuration software, you can aim the sound beam to exactly this plane where the people are standing here in the departure hall of an airport, for instance. Avoiding all these hard materials like the ceiling, which is metal, and the glass and the floor. How do you do that? Here's the configuration software where you can calculate the distance of the room, even if the floor is tilted, for instance. And then you can aim the sound beam like you see in this picture. You can aim it exactly at where the people are sitting. Okay, delayed arrivals. When are they a problem? They can be a problem if you use highly directive loudspeakers, like for instance horns or arrays. And if you install these loudspeakers at a certain distance out to each other, like for instance in a tunnel. Now, what does it do? What do these delayed arrivals do? They will arrive at a later time at a certain position. Like here, you can see in this example from a tunnel. We'll have the initial sound coming from this loudspeaker, and the sound travels all the way up to this tunnel. And then it meets the second loudspeaker installed here. That means that if the sound coming out of this loudspeaker is in sync with the sound that's coming out of this loudspeaker, then you will hear the initial message with a certain delay coming out of this loudspeaker, the initial one. Now that will have a bad influence on your intelligibility because it will interfere with the message. You will hear it as a kind of an echo. Now what can you do? You can delay the sound at the second loudspeaker here, for instance, with a certain time. You know, sound will travel with about 340 meters per second, so you can calculate the distance here, and then you can say, okay, after maybe 10 milliseconds or 20 milliseconds or 100 milliseconds, the sound from this loudspeaker will arrive at this loudspeaker. So we'll put a delay here in this loudspeaker with, for instance, 100 milliseconds, and at the time that the initial message will reach this, then the same message will be audible from this loudspeaker as well. So they're totally in sync and they can support each other instead of have a negative influence on the sound. So one thing that you have to keep in mind, if you look at this picture over here, all these loudspeakers have to be driven by an individual amplifier. So you need a direct topology. You have to have a system with the DSP inside, and direct topology, that means that every loudspeaker has to have its own amplifier. A direct topology is, let's say, available in Presenza. So Presenza can be used for these kind of applications. They will have dedicated amplifier outputs and the DSP inside with the delay check you see here, and this is from the configuration. You can set a delay up to 60,000 milliseconds, 60 seconds, so that can cover an area of almost 3.5 kilometers. So that's quite a large area. Okay, then the final and important part is speech intelligibility. How do you measure this actually? How is this done? How do you know when something is intelligible or not? Now, one way to do this, how to measure this, is by a perceptual test. So somebody talks and there's somebody listening, and that person or those persons will write the word down that you have spoken, and after a certain while, after you have done a certain amount of words or sentences, then you will check if that person or those persons have written down the right words. So then you can say, yeah, you have understood maybe 80% of what I said. That's an indication of your intelligibility. But you can imagine this is quite costly and time consuming. You need a lot of people to test this. So it's not really a good way, or let's say an efficient way to check the intelligibility. So they have invented these predictive tests with measurement equipment. Yeah, you can do that with well, measurement devices like here, where you can measure the STI, the speech transmission index. Now this was actually from 1988 when the STI room acoustics became the international standard as described in the IEC 6268-16. And then Bruel and Kier, they introduced RASTI, a rapid STI measurement device that could do a STI measurement in less than 30 seconds. So it's, let's say, a rapid STI, it's faster than the full STI, so that was already a big improvement. So in 30 seconds, within 30 seconds, you could do an STI measurement. And in 1999, the Speech Transmission Index for Public Address Systems, STIPA, was invented, and this is now becoming, let's say, more or less the national standard in the different countries for voice evacuation equipment. And you can measure this, so this STIPA, with a handheld device, for instance, like you see on the picture here above. Now, what does this measurement do? It's actually measuring the loss of modulation at 98 coefficients, like you see here in the table on the right. So it will measure that for several octave bands from 125 Hertz to 8000 Hertz. So that's the area most important for speech. And it will do that for different modulation levels you see here on the column on the left. And then it will add all these values up. And then on the bottom, you see the modulation transfer indices. So that's the average of all sound pressure levels that are measured for these octave bands. Now this is a real measurement, so it will take all these things like reverberation, signal to noise, your threshold, your hearing threshold, masking effects of frequencies. It will all take that into account. Now, what does this measurement device do? It will not take measurement of the full matrix of all these points, but it will take only 12 points spread over these measurements. And the result of that measurement is called STIPA, STI for public address, instead of full STI. Yeah, you need, in order to test this, you will need a special test signal, a modulated test signal, in order to reproduce these octave bands and all modulation levels. Now, if you buy a measurement device like this, you will get this modulated sound level or sound. You will get that with it. I can maybe play it so you have heard it once. It's a real awkward signal. Maybe I can play it just a second. We'll look for a wave file. Yeah, here it is. Now, listen, this is the STIPA sound. Was that audible, Maarten?
Yeah, yes, it was, and I confirm it sounds weird.
It's weird. Yeah, it's a modulation of all these octaves, all these frequencies. yeah, what you do, you will have to run this sound through your sound system and then take those measurements with it, and that's how you can do these measurements then with this measurement device. Okay, then the range of STI ranges from 0 to 1. Now 0 is very poor and 1 is excellent. Yeah, that's the best you can get. In general, a value, an STI value of 0.5 is fair. It's good enough for voice alarm systems, and 0.45 or 42 maybe for difficult environments with long reverberations and high noise levels, like in tunnels, for instance. Now, be aware. In theory, the maximum achievable STI is 1.0, but okay, yeah, you always have noise or reverberation in the room, so that's in theory the maximum you can reach. But the lower the sound pressure level is, the human ear cannot hear that anymore, so due to lower sound pressure levels. So you can see here on the graph on the right side that the STI will decrease. The human ear will not be able to hear those low sound frequencies, sound pressure levels. And also, what they found out, let's say later on when this STI standard was approved, that when the sound is higher than when the sound level is higher than 85 dB, also your ear will suffer from a factor that it cannot hear as well anymore. So yeah, you can see that in this graph. The higher the sound pressure level is, in the previous day they thought, okay, from 55 dB, then it will be a straight line. Your ear will be able to reach an intelligibility index of 1, but that's not true. So they have adjusted it, matching this graph over here. Now there are different ways to measure intelligibility. One is the Alcon's method, the articulation loss of consonants, and the one I just already mentioned, the STI speech transmission index. And we use STIPA, the STI for public address. And all these methods are combined in a common intelligibility scale. So you see that on the right side, there are different ways you can measure the intelligibility, and they're combined in a common intelligibility scale. Now you can see here in the green area above 0.7, on this scale here, from 0.7 you can reach 0.5 on the scale of STI. So this is STI index. That's those circles. So you follow this line. You can see here it's at 50%. So that is 0.5 on the STI scale. If you look at the Alcons, the articulation loss of consonants. Low loss of consonants, of course, means good intelligibility, and there's a way to calculate this, taking all the acoustics and the electroacoustics into consideration. Yeah, be aware that bad room acoustic conditions cannot often be solved with electroacoustic means. So if you look at this equation over here, you see the RT60, the RT60 time is in it, and also below the directivity of the loudspeaker, and that's actually the only factor that can influence this index. Now, what does the directivity mean? Okay, it's the directivity of a loudspeaker. If you have a loudspeaker with a directivity factor of 1, that means that this loudspeaker is radiating all around it. So like a sphere, you see here on the picture on the right, Q factor is 1. That means it's all around the loudspeaker, and this also the DI index of 0 dB, the directivity index. Then if the index goes up, if the Q factor goes up, a factor 2 means that it's only half. The loudspeaker will radiate only to the front, for instance, like you see here, half of the sphere. And that means that all the energy compared to this loudspeaker is now put into this area over here. So that means the half of the area to cover is now, well, basically twice the energy. So the directivity index will be 3 dB. And for a quarter of CQ4, you can see it's only a quarter of that sphere, and so on. So the more directive a loudspeaker gets, so the higher the Q gets, the more directive it is, and the energy of the loudspeaker will be concentrated more and more to the front of the loudspeaker, and makes it more directive. So you can aim that energy to the listening plane. Now, if you look at the STI, the higher the STI, the better your intelligibility is, like you see here on this graph. So theoretically, 1 is the best. Now, if you look at this equation, also here you see the directivity Q, and also again the RT60. Now, this is the only the Q factor is the only thing that has influence on this STI, and the RT60 here you can see it's squared is taking a lot of portion of this STI. So the higher the RT60 will be, the worse it will be for the STI. So now the conclusion here is that yeah, you cannot really fix bad room acoustics with electroacoustic means. So if you see this here, the RT60 time, if that is high, you cannot fix that with electroacoustic means. So the thing to do then is treat the room with absorption material, for instance. Okay, for the design of a sound system, what you have to keep in mind, yeah, again, the distance between loudspeakers and listeners, the sound pressure level has to be good. So you have to know what the performance of a loudspeaker is, how much sound pressure it can deliver, and at what distance from the listening plane it has to be installed. And then also the number and directivity of the chosen loudspeakers. So yeah, if the distance gets shorter and the Q gets higher, a lot of sound sources must be used. But then also the N factor, the amount of loudspeakers becomes in play. So that is also then again a negative influence on the equation. Yeah, each audience area should be reinforced with one main loudspeaker. Otherwise, you have effects like interferences from other loudspeakers, echoes, and reflections. So you have to be aware of where to position each loudspeaker for a certain area. And then, yeah, of course, the directivity, like you see the Q factor here in this equation is most important. So yeah, you choose the loudspeaker with certain Q in a way that the directivity allows you to cover this area, like we have seen before with the column loudspeakers, for instance. You can aim it at the people where they are sitting or standing, avoiding the reflections from the walls or the ceiling or other surfaces. So Martin, that was basically it. I hope it was all clear, but maybe are questions.
Yeah, I guess it's a lot to take in, but thank you anyway for this. Very interesting. Yes, there are some questions. One of the questions is, what are the parameters you can give to your sensing microphone? Like, I mean, the value over X seconds, or an instant value before announcements? That relates to slide 25.
Well, it all depends what system you use, I think. If you have a measurement device like an NTI, you will just take a measurement and it will be well, a certain period of time. It also has to do with how you measure things. Do you measure with people in a room, or are you measuring with no people in the room? You can combine those two. But yeah, I have no indication of time, to be honest. At a certain moment, I guess the level of sound, it will not change that much. But I cannot give a clear answer on that, to be honest.
Okay, thank you. Another one. If you have a car in a tunnel as shown, built in concrete, what kind of loudspeaker would be good to use, considering it also needs to be waterproof?
Yeah, there are special tunnel horns for it. So horns that you can mount to the ceiling or to the side of the walls. So yeah, horns. You use horns in tunnels.
Okay. Then related to slide 42, this is information. It is now possible to measure full SDI with handlet devices, Bedrock Audio. Also, Rusty is no longer used or recommended to use in public spaces. So this is just an additional comment. Thank you for that.
Yeah.
Slide 49. Does your equation take into account the number of speakers, and is it N? I think you answered that on
Yeah.
the last slide, right?
Yeah.
The N stands
Yeah.
for the amount of speakers.
Yeah, exactly.
Okay. Then there is here a question which I do not really get. Sensitive microphone installed with the system, not the NTI measurement used for evacuation. I don't understand. Maybe you can rephrase this question so we can still answer it. Okay. Regarding the question, what are the parameters you can give to your sensing microphone? That's the one, the question we talked about before. And then sensitive microphone installed with the system, not the NTI measurement used for evacuation. Do you understand the question, Jan-Pieter?
Oh, sorry, I don't understand the question. Sorry.
No, I don't understand it either. Yeah. Okay, this was also the last question on the list. The slide 25, if you could go back. This is a question, Jan-Pieter. Can we go to slide 25? And then maybe you can rephrase the question once more when we have the slide on the screen. Okay, slide 25. Yeah. Now, let me see. Sensitive microphone installed with the system, not the NTI measurement used for evacuation. This is now. See, regarding the question, what are the parameters you can give to your sensing microphone? Okay. What parameters does the ANS have? Yeah. Okay.
Yeah, okay. What you will have to do, you make a measurement in a room when there is noise, so that level is the basis of your like you see here, for instance, on the right side where you see the graph from the Vari. That is your ambient noise. So that's the default level. Then if the sound let's say you measure a noise, ambient noise level of 70 dB. Now, if the sound is, let's say, increased with the ambient noise is increased with, for instance, 6 dB or something like that, then this loudspeaker, the volume of the loudspeaker will go up in order to stay ahead of above the noise floor. So it depends on the room where you measure this. You measure your noise. And then you say, okay, if the noise increases with, for instance, 6 dB, then you also increase the volume.
Yeah.
So yeah, that totally depends on the room.
Yeah. Are there also other parameters which you can set in the ANS sensor?
Yeah, there are different parameters you can set. I think it's also the time. You can see maybe here I have the picture of the Vari. Let me see, no, this one, the one before. Here. There is a for instance, a time that the noise level has to be increased. Otherwise, you might get the situation that the AUC starts increasing and lowering the volume all the time. So you get loud and then less loud. You know, so there's a time indication. Yeah, of course, the range that the volume has to be increased, like you see here, 6 dB, and
Yeah.
the slope that it will go from yeah, let's say -6 to 0 dB in steps of yeah, increasing the SPL level, the volume.
Yeah. Okay.
So yeah,
Hey, I also see that just look in the data sheet that the ANS sensor also has two different modes it works in. So one is a sample and hold mode, and the other one is a tracking mode. And the sample and hold mode basically means it measures shortly if it needs to make an announcement, let's say at the railway station.
yeah,
It makes a sample of the ambient noise level at that specific time, and then it adjusts the sound pressure level according to the ambient noise sensor level plus, let's say, 10 dB. That's the sample and hold mode. And there is also a tracking mode, which is a mode more used for background music, where it is on the fly adjusting the sound pressure level accordingly to the measured ambient noise. So
mm,
this is also something which the sensor does.
yeah,
And
yeah,
four sensors can be combined to cover a large area if you have a bigger zone. And I also see it has some integrated DSP options that come with those two tracking modes. So
yeah,
if you want to have
yeah,
more details, you can also look into the data sheet. It's described extensively there, also with the different mounting options that we have. So yeah, I hope that is answering the question.
yeah.
Yeah,
It really depends on the system. Like in Presenza, it's more specific. It works differently than the Vari that I just showed you. But okay, different parameters you can use.
yeah. Okay.
Back where I was.
Yes.
Any other questions, Martin?
No, we just got a thanks, so I think the question is now answered. No, this was the last question. Yeah, this was the last webinar for this year, but it's not the end of the series. So we will continue next year, 20th of January again. Hope that you will again join and learn more about the basics of the PA. Jan Peter, thank you again for this interesting session. And yeah, I wish you all good holidays, stay healthy, and then hope to see you again, or yeah, that you participate again in the next webinar on the 20th of January, and then we will talk about loudspeaker planning for your project. Okay, thank you very much. Have a good day. Bye bye.